Hello students, here is a quick review on waves for the final exam. There are 6 to 7 questions from this chapter, so pay attention to everything that I'm saying. Now, waves is actually a transfer of energy through a material. And when energy goes through a material, there is a speed at which it moves. So the speed or velocity of the waves is given by the formula frequency multiplied by wavelength. F is the frequency and lambda is the wavelength. Now frequency is the number of waves in 1 second, while lambda is the length of one wave. So therefore, if the frequency is 500 hertz, and the wavelength is 0.2 meter, we can calculate the velocity of the wave simply by multiplying 500 with 0.2, which gives 100 meter per second. So that's a basic formula for speed of a wave. If we consider a particular situation of a string that is kept stretched under a tension, then the formula for speed becomes square root ft by m. So this is only applicable to waves traveling along a stretched string. In this case, ft is the tension, so how tight the string is, and it is measured in newtons, while m, you got to be careful about that. That is not just mass, it is the mass of 1 meter of the string. M is the mass of 1 meter of the string. So if the tension is given and the mass of a particular length is given, you have to first calculate the mass of 1 meter of the string. Okay, again, m is the mass divided by length, so it gives you the mass of 1 meter. So let's assume that the tension is 150 Newton and the mass is 10 gram, and this is the mass of a length of 5 meters. So first up, you have to notice that the mass is in grams. You have to change it into kilogram. Now to change gram into kilogram, you divide by 1000. So 10 divided by 1000 is 0.01 kilogram. So the unit is now kilogram per meter. And once you do that, you plug it into the formula and you get speed is square root 150 by 0.01, which gives you 122 meter per second. It's as simple as that. Next, let us look at the basic construction of a wave. There are some basic definitions that you need to know. You need to know that on the x-axis you have distance, on the y-axis you have displacement, which shows how far the particles in the material are moving. Okay, so both are in meters. But the maximum displacement is called the amplitude. The maximum displacement from the undisturbed position, which is this one, the maximum displacement is called the amplitude. Wavelength. Wavelength is the distance from one crest to the next crest, or from one trough to the next trough. Or in other words, it is the length of one wave. So if you start from here, that's half a wave, and then you have the next half. So that's the length of a wave. This is the length of a wave. So when you measure the length of the wave, you measure it along the x-axis. That is the length of a wave, which is exactly this. It's represented by lambda. So if you look at this diagram and assume that the distances are here at 0, here at 0.2 meter, 0.4, 0.6, and 0.8, what is the wavelength of this wave? Well, this is at 0.1 and this is at 0.5, so the difference is 0.4. Or you can just take the length of a wave. See, remember, that's the length of a wave. So either way, the wavelength is 0.4 meter. Now I have the markings for the amplitude. So you know that the amplitude is 0.3 meter. 0.3 meter. It can be plus or minus because the wave goes up and down. And incidentally, you can also calculate the velocity like we did before. If the frequency of this wave is 100 hertz, what is the speed? We did that before. Just multiply the frequency with the wavelength. Also remember that there are two types of waves, a transverse wave and a longitudinal wave. What type of wave is this? It is a transverse wave. We're going to look at it again, but just wanted to tell you that in a transverse wave, the particles oscillate up and down while energy moves along the x-axis. So particles move along the y-axis up and down while the energy moves along the x-axis. So that is a transverse wave. Next, let us look at harmonics. So here is the vibration in a stretched string. So you clearly see two segments here. There is one segment here and the second segment. If there are two segments, it is called the second mode of vibration because there are two segments. And this is lambda, so that's the wavelength. But if you look at this diagram, this is just one segment. The whole string is vibrating as one segment. This is called the first mode of vibration. So if there are two segments, it's the second mode of vibration. If there's one segment, it's the first mode of vibration. The first mode of vibration is also called the fundamental mode. Let's assume that the frequency is 200 hertz for the first mode. Then for the second mode, it will be 400 hertz. What about for the third mode? Assuming that all other conditions are the same, the length of the string is also the same, then for the third mode, the frequency would be 600 hertz. Now, these multiples of the first mode frequency are called harmonics. So the first mode is also called the fundamental frequency. So if the fundamental frequency is 200, then the harmonics are just going to be multiples of those. So 2 times 200, 3 times 200, 4 times 200, and so on. You cannot have any other frequencies in between. So in this particular case, it's impossible to have 150 hertz or 50 hertz. You cannot have an harmonic like that. Next, let's talk about the interference of waves. So waves can come together. Two different waves can occupy the same space at the same time. As shown in this figure on the left-hand side, if the two waves have their positive amplitudes coinciding like this, you see the positive of both. So this is the first wave, this is the second wave, and these two waves are in phase with each other, P-H-A-S-E. What do you mean by in phase? That means their positive amplitudes coincide, so do their negative amplitudes. And if these two waves come together, they produce constructive interference. That means the amplitude doubles. You can see this. This is the wave that results from these two coming together. That's constructive interference. But on the other hand, if the two waves are out of phase by 180 degrees, what does that mean? Where you have the positive amplitude of one, exactly at that point you have the negative amplitude of the other. And the negative with the positive, so they cancel out completely. This is called destructive interference. So there are two types of interference. One is constructive interference, the other is destructive interference. Now, incidentally, in noise cancellation headphones, this is what is used to keep the outside sounds cancelled. So you only want to listen to the music, so you cancel out the noise, the outside sounds. Like when you're listening to music in an airplane, you do not want to hear the noise of the engines, so that's cancelled out. So remember, there are two types of interference, constructive and destructive. Now, the next topic, we already spoke about it. There are two types of mechanical waves, transverse waves and longitudinal waves. You're going to see the picture, and then you know that in a transverse wave, right there it is, in a transverse wave, the particles are moving up and down along the y-axis, while energy is moving along the x-axis. So when this slinky is moved up and down, energy goes along the x-axis, but the particles of the slinky are moving along the y-axis. That's why it's called a transverse wave. On the other hand, in a longitudinal wave, particles vibrate along the x-axis and energy also moves along the x-axis. So that's why here you see particles oscillate in the direction parallel to wave propagation. But for a transverse wave, particles oscillate in the direction perpendicular to the wave propagation. So that's the difference between longitudinal and transverse waves. Sound waves are always longitudinal, while light waves, they are not mechanical, they are electromagnetic, but they are transverse. So light waves are transverse, sound waves are longitudinal. And the last topic that we're going to discuss that you need for the final exam is how to calculate the intensity of sound. Now, the intensity of sound is calculated in a unit called decibels. Decibel. So the actual unit of intensity is watt per meter square. So we need to know how to change from watt per meter square to decibels. Here is a formula. Beta is the intensity in decibels is equal to 10 times log I by I naught. Now, I naught is called the threshold of hearing, which means it is the lowest intensity that human beings can perceive. And the value is 10 to the negative 12 watt per meter squared. So that's the lowest intensity of sound that we can hear. So if I is 10 to the negative 11 watt per meter squared, how do we calculate that in decibels? Just plug it into the formula. So I is given as 10 to the negative 11, so you substitute it there. And I naught is always a constant. You need to know the number is 10 to the negative 12. So when you do the math here, you see that you're going to get 10 here. If you don't believe me, put it into the calculator. You're going to get 10 here. And then when you take the log of 10, you get 1. You're not taking the natural log. Be careful. On the calculator, you have natural log, which we are not using here. And you also have simply log, which means log to the base 10. That's what we're using here. So log to the base 10 of 10 is 1. Therefore, in decibels, you're going to get 10 times 1, which is 10. So 10 to the negative 11 watt per meter squared becomes 10 decibels. Let's do one more. So you see what the correlation is. What if I is 10 to the negative 10 watt per meter squared? So that means it's 10 times more than what we took before, right? Then you're going to get log to the base 100. I have not written all the steps, but you can easily understand. And that will give you 20 decibels. So look at that. When the sound intensity actually increased by 10 times, the sound intensity in decibels just doubled. See that? Just doubled. So the next question is, if the sound intensity increases 100 times, by how much will it change in decibels? It'll triple. What if it changes 1,000 times? Then it'll quadruple. So you see the correlation there? Keep that in mind, because that's a question on the exam. So that's all I had for you from this section of waves. I'm trying to make it as precise and concise as possible. And hopefully you're listening to it many times, and surely this will then help you on the exam. Thank you.